Okay. We're going to get a vector field that's radial from the origin. So we want to x, y that's radial. Means that all the vectors are along a radial line. Every vector is along a radial line. So I said, well, you know, we could start just by saying if you have a point x, y, how would you write the condition that the vector at x, y is radial? Okay, in other words, f of x, y would be radial. But just think of one point, any point, okay, without specific coordinates in terms of x and y. If that's a problem, you simplify the problem a little more. You get a grasp of it. And you say, okay, let's just take any point. I just wrote down 3, 7. If you can't do this, you can't do this, try it away, try this. Once you do this, then you probably do this. And once you do this, you've pretty much done this. But you wouldn't know that when you were solving an unfamiliar problem. Okay, solving an unfamiliar problem, go to a specific point and try to make it work for that point. Or if you can bypass that, fine. Okay, it took a couple of minutes, but and we didn't quite get it because we had this picture. And that picture was written down real quickly. Okay, and if you got this picture, then you can write down this vector because there's already a picture of that vector. Trying to do vectors probably would have been a good idea to write this down. You didn't have a 3i7j on it, you had a 3 and a 7. It was right there, smiling at you, and you failed to smile back. Because you got off on a sort of a tangent, not mathematical tangent exactly. With all this stuff, because you're remembering something you did almost right on a problem. Okay? Your denominator had a 3 halves power instead of some other power, or something like that. Okay? It was you know, pretty good solution, just wasn't quite right. You want to make sure we get that right, and you might want to review that problem that you did on. Okay? Because, like I said, you were that close. Well, okay, anyhow, we've got this, right? So that works for 3, 7. Now, how would you do a vector, a radial vector at x, y? So let me pause here and then you get back up to the board. Okay, now we've conjectured that xi plus yj is radial. I didn't really do a picture and didn't really prove it, but it's real easy to picture it. Here's the point xy. So here's xi. Here's yj. And that's pretty small. Okay. And you call it about it right here in the vector. Okay. So that vector would be radial at this point. Now we would maybe draw that like so. Up here, got the point 3i7j, and we want that vector to be associated with the point 3, 7. Well, we probably draw the vector originating from that point. Now, I didn't quite get that right. It should be pointing directly away from the origin along the radial line. Okay. So there is the vector 3, 7 at the point 3, 7, right? And we could have the vector on xy. You have a point this long directly away from it. Okay. There's xi plus y. Okay, well, how about we draw vector xi plus yj on this picture? Okay, and I'm going to say draw them on this circle. course, there's some little labeling. But go ahead, I'll let you use the blue chalk because this is a special thing. Okay, actually, you're going to color you want it, but see if you can sketch what that vector field would look like. Okay, well, got a pretty good picture finally. Okay, first thing, you know, you wanted to try was draw the vector from the origin. Okay, well, clearly that is what I did. Just try to draw each of these vectors from the origin. Then the vectors to here and the vectors to here are going to look, it's going to overlap each other, and you're not going to know where any one of them really comes from. That would be putting the head at the point. You want the tail of the vector to be at the point. So it's got to be like this. You can draw this vector from the origin, at least in your head, but then you want to put it out. So now if you do that, well, everything looks like this. You got radial lines, the vectors are all in the direction from the origin to the point. And if it's xi plus yj, well, you got square root of x squared plus y squared equals 1. On a circle, okay, square root of x squared plus y squared is going to be the square of the radius of the circle, right? So that the length of the vector negative x y, which is negative x I plus yj. Is equal to the distance. Okay. Okay, well, now. What's the gradient of that vector? Of course, the assignment you did before this recently was due, I was on conservative vector fields. Okay. And you've been even previously introduced to the del operator. Now, this is totally fundamental. Use that basically gradient operator. Okay. When you apply it to a scalar. Okay. So another thing that I'm a little surprised hasn't been locked in. Okay. It's a major thing. Maybe the most important concept we've seen today. Okay. So that is locked in. Think about how you're taking notes, how you review, how you read. Okay. So not for the comment. So go ahead and see if you can do that del dot F now. Okay. Well, now, having written this down, and kind of had to prompt people that are, you know, right? You got this dot this. Well, you're going to automatically write this, which is out here, and you're going to write this, which is here. Okay. There's a lot of hesitation of writing that. I'm not sure what it was. But once that was done, okay, the dot product was done correctly. Could be simplified, but everybody knew what it's simplified to. But you want to write it all out. So you get this expression, partial respect to xi dotted with this, okay? And of course, you didn't write the partial respect with respect to x times I dotted with this. Okay, so let's make sure we understand all that. So I kind of insert that wherever I can. Ended up not being able to see. Thanks for writing. So high cost, good, high end, good. At least that's kind of what I think of as using your notation. Now I would just say, go you do the partial. Well, let's just start it off. Partial respect I applies to both of these. Okay, so there's a distributor law. All these laws apply. It should be. Somebody should ask you to prove it. I'd ask you to prove it, except I thought the Web of Science assignments were heavy enough. There's some things I wish I'd have done differently. But okay, well, this means you got, first of all, the I's are like constant vectors, right? So the constant quantities, again, these are properties of dot products. But you get partial x with respect to x times I dot I plus partial of y with respect to x times I dot j plus partial of y, partial of x with respect to y times partial with respect to y. So this term plus with respect to y of x plus with respect to y of x times I dot I plus the partial of y with respect to y times j dot j. Okay. Now, this and well, this is 0 because I dot j is 0. Okay. So that's 0, one reason. This is 0 because the partial of x with respect to y is 0. Okay. Maybe you need this and this. I dot I is 1, partial of x with respect to x is 1. So this gives you 1. And partial y with respect to y is 1, j dot j is 1. Okay. Now you told me that this gives you 1 and this gives you 1. But the reason it gives you 1, you have to understand the reason it gives you 1. And it really proves to me that you know why that gives you 1 instead of just a lucky guess. It's more than a lucky guess, but you know, I can't distinguish unless you show me. Give me some explanation. At this point, you should have calculated a bunch of, well, del F for scalar functions. Okay. But now we've got to get del dot X. Okay, so let me ask you to quickly calculate. Big difference is they want wholesale launch interacting with far fewer people, a whole lot this, which is a different type of thing. In other words, over here, in what we just did, we got a number. What are you going to get when you do this? Okay. Now, I had a little more trouble with this than you should have, but mainly because of just a couple of things. Some really important things. Okay, first of all, we wrote out the distributed block correctly. That's good, good start. Then you have one here and one here. You have I and J. Okay, but look, I is like a constant. You anchor it out here, and then you have partial of x with respect to x. That's one, right? So you get an I, not just a one. Okay, now of course that's written out over here. And then that was after I had to point this out. Okay, and then the partial respect of y of j times y. You factor out the j, the constant, and partial y with respect to y is once you get j. So wanted to write down 1 and 1 because, of course, what we did before, you were doing a dot product, and I dot I is 1, and J dot J is 1, right? There's no I dot I here, and there's no J dot J here. Okay? So what I'm saying is you just haven't calculated enough of these the whole section. Okay? You really got to go back and just do a bunch of fundamental calculations to get these things in your head. Because we're all the way up to Green's theorem, but we're kind of in trouble there. Okay. Figure out what to do about it, but and then you have this partial y with respect to x times I, partial of x with respect to y times j. You wanted to write out this, okay? And didn't seem to understand that that's 0 and x. Now, when I ask you to do this, then you need to treat y as a constant, right? You take the partial with respect to x. Well, if you treat y as a constant, your partial with respect to x is going to be partial constant root of the constant 0, right? So that should be automatic. If they understood that in this context, this is transferred in this context, because you're not quite thinking it through, but you know, I mean, you do this, that's pretty good. Okay. You know what the rule is, you just can apply it. Okay, so anyhow, you get I plus j. So if F equals there it is. Okay. It's a vector. Okay. That gives you gradient field. Okay. So if F of x1 equals I plus j, get to that vector. Okay, now y'all got a little bit rutted in your thinking. Your mind is running in a rut. The rut established by the last problem, okay? Which has nothing to do with this. Okay, you want to draw radial lines and all that stuff, okay? And it just wasn't working. So, you know, show me I, show me j, show me the vector I plus j, right? On this scale, where this is implicitly 1, and this is 1, here's 1. There you have it here. Okay, right here, 1. I here. Right here. Okay. Well, you finally got it right. Okay. Vectors on this way, vectors on this way. What's a radial? It's not radial. This is constant. It's the same everywhere. Radial changes direction. That's important. What I hope I have time to say that. There's I. There we go. Same thing here. Same thing here. We'll give a take this down. But we're not evaluating this. And these vectors, well, those are nice radial vectors. Okay. But they have nothing to do with this. Now, this one might well be. This and this and this. Okay. So the vector field. All the way up, all the way down, and all the way over. Okay. It's mad. All space filled by these that well in the plane. Okay. Imagine a plane with these vectors. Actually, you can do it in all space. You have to choose your X, Y, Z axes. Whatever you want to do, kind of coordinate system independent, but that's much more advanced. Okay. Okay, well, that's this vector field. Now let's go back to this radial vector field. It could pretty well be put together. What I want to do, okay, is this field conservative? How do you determine the field conservative?
See what I'm saying, right? You say, hey,
All that F is 0 at every point. You're equal, but always equal. That's conservative vector field. So look at conservative vector fields in physics. They're extraordinarily important. Magnetic fields, gravitational fields. We're about to start gravitation. We're going to use a lot of these properties, but we're not going to use the multivariable calculus, although I'll refer to it because it helps understand the multivariable. And of course, understanding this gives you a broader perspective of understanding physics. Okay. Now, if I wanted to do a line interval of this field around, let's say, let's start around this stuff. Oh man. Okay. This path. Can you do the line interval? This is the curve C. Let's let the curve go clockwise. Not going to draw there on this little stuff. That's too fun. Here's your curve C. There's interval over C. F dot dx. Okay. Well, first of all, on the surface, this is radial, so the field is always perpendicular here and here, right? Okay. So you're going to get 0. Because your displacement vector that way. Okay. What about here and here? Well, that's just a question. I'm going to do that anyway. I'm going to set it up. Pretty straightforward. In terms of what we did before, because we talked about an integral of an arc of a circle, right? So here's an arc of a circle, here's an arc of a circle. Here, a couple of straight lines. You got it polarizing. Okay. So think on that. I want to do a lot more with this, but we haven't yet worked through details of the gradient. Okay. The divergence. This is called divergence. Green's theory talks about how the integral of the divergence over this region is equal to the flux of this field. Okay. And we want to develop that and take a glance at what's in the board there. That's okay. Save that last review before I remove it. Okay. Because it's one of the really neat things in this course. I just couldn't bring myself to wash that board. But finally, once you guys get this, I'm going to get to wash this board, right? Okay. So